second. The bottleneck was sourcing a laptop that could display PDFs, surprisingly. Okay, there we go. Right, yes, so can you all hear me okay? I guess you can hear me at the back? Good. Yes, so as John said, I'm Sam Pallister, and as you can probably tell from the big beard and bleary eyes, I'm a final year PhD student. And I want to start with an apology, mainly for breaking our streak of preeminent Peters in this session. Clearly Peter Shaw couldn't make it, and you're stuck with me instead. Yeah, so I'm in the business of verifying quantum states. So what that means is that I sit at the very end of the production line that represents a quantum experiment, and I'm really interested in the data and the statistical inference you can make from measuring outputs from quantum experiments. And I'm going to give you a flavour of the kind of research I do, but most of it is in this paper on the archive from back in September, so if you really want to know about results, come and talk to me afterwards, or go take a look at that paper. Okay, so what do I mean by a quantum experiment abstractly? Well, this is the theory session, so I'm going to give you the theorist's picture of what a quantum experiment is, and it looks like this. So this is any quantum experiment, is this box that's claimed to produce some quantum state. So this state could be absolutely anything. It could be some resource state that you need for quantum computation, or some noon state for metrology, or whatever the hell you like. And the goal is to take a box that's claiming to produce lots of copies of this state. You push a button and the state comes out. And to make some statistical inference about whether the state that's coming out is actually the state that you want. So typically, what would you do in this scenario? Well, a run-of-the-mill thing is a box that looks like this. So you take your box that is an experiment and you plug it into a box that does some measurements and some analysis for you. So I call this box C because it's a characterizing box. So something that might fall into this category is something like state tomography or something. So you have some experiment, it claims to produce some state. You do some tomographically complete set of measurements. You get some inference about what you think the most likely state coming out of your experiment is, and you compare it to psi, and you see whether it's the actual state you wanted or not. And that's a very common thing to do if you have any experiment that's claiming to produce any quantum state, but it's not the only game in town. So there are a couple of other things you could do. So you could just plug it into a box that spits out a single number, rather than a long tomographic list of data. So maybe you can directly estimate the fidelity of the things coming out with the target state that you want, without having to resort to tomography. That would be nice. So rather than having these screeds of data that correspond to tomography and having to do some complicated data analysis, maybe you could directly estimate a fidelity or something, or maybe you could do an entanglement witness, or you could get some partial information about the state that's coming out of your experiment and how it compares to psi in a way that doesn't resort to tomography, possibly. Or even more simply than that, you could worry about a verifying box that looks like this, that knows about what target state you want. And in this scenario, rather than outputting screeds of data like in tomography, or a single number like a fidelity estimation box, it just outputs a single bit, right? So I want you to imagine you get your experiment, you plug it into this box that has two lights on top, you feed in lots of copies of your state that's coming out, and if you get a green light, then you know that the state that's coming out of your experiment is exactly psi. If you get a red light, then the state that's coming out is not psi, right? Now, if this red light goes off, that's bad news. It's bad news because, well, A, you don't have the state you want, but B, you learn nothing about what state you have. So in that sense, it's different to tomography. If in tomography the state that's coming out of your experiment isn't exactly psi, but it's some other state rho, you at least get some estimate of what rho is. But for these boxes, you don't get that information. If you get a failure case, you learn basically nothing. But the advantage that you gain from having a simpler verification scenario is that they're going to be cheaper to implement. So typically tomography is prohibitively expensive to implement in terms of number of qubits of the state that's coming out of your experiment, scaled exponentially badly. And I'm going to try and convince you that these things further down are much cheaper to do, at the expense that if you get a failure mode, then you learn very little about what's going on. Okay, so I'm going to spend the rest of the talk talking mainly about boxes down here, and I might dabble in boxes in the middle. Okay, so that's a rather abstract picture of what I mean by a verification box. So can I give you an example? And the answer is yes. Here's a really simple example. So imagine you've got an experiment and it's claiming to produce psi. So you push a button and you think a state psi is coming out. So what you're going to do is you're going to take every copy and you're just going to project onto psi. Right? So let's label these measurement outcomes plus or minus, and one of two things can happen. Either you get a long string of pluses, in which case you very rapidly build up some statistical confidence that your experiment is outputting psi, or something very, very close to psi. Or you get a string that looks like this, that has a few minuses thrown in which case you know that you're not exactly psi, and you very rapidly can lower bound how close you are to psi in some of this. But under the proviso that if you get any minuses in your string, you learn nothing about what the state actually is, only that it's not psi. Okay, so what kind of statistical inference can we make in this scenario? Well, here's the kind of parameters that we're interested in. So there's the number of copies, the number of times you push the button on the top of the experiment and the states come out. And the more pluses you get, i.e. the more measurements you take, you increase your statistical confidence that you're close to the state you want. Right? There are three parameters involved. There's the number of times you push a button and the state comes out, let's call that little n. There's this statistical confidence, which I'm not going to talk about too much. And then there's this distance parameter, let's call it epsilon, how close you are to the state you want. So all these verification protocols will just be defined by some relation between the number of times you have to push a button on top of the experiment and how close you can say you are to the target state you want. Okay, right, so it turns out that this protocol, even though it's very, very simple, is actually the very optimal verification box you could apply to any state psi. Right? And that's a very simple proof. I'm not going to go into it too much now. But the problem is that it's very hard to implement in practice. So this measurement psi, this state, could be some horrible non-local or entangled state. And so you may be working in a scenario where projecting onto this state is impossible, i.e. if psi is distributed and the different parts of it are space-like separated, then this thing is something you just can't do physically. Or you might be working in photonics and this measurement is probabilistic. There's going to be some failure cases. And in fact, the more this n increases, the exponentially decayed probability that all these measurements pass. And in general, in most platforms, it's very, very difficult to do a measurement in any entangled basis. So it'd be very, very nice if I could write down a box like this that doesn't involve a measurement that's so damn hard to do in the lab. So I'm going to convince you that, hopefully, you can do protocols like this for boxes that are more easily implementable in the lab. So here are some requirements that we might insist on. So one for you and two for me. So here's one for an experimentalist. So I'm going to assume that all the measurements you can do are local. So no entangling or non-collective basis measurements like this. You just do some local measurements. And the measurement's going to be non-collective. So you don't press the button lots of times, store up lots of copies and measure them all at once. You push a button, you get a state out, you measure it, you throw it away. You push a button, you get a state out, you measure it, you throw it away. etc. And two for me, just to make the maths easier, I'm going to assume that your measurement devices are perfect. And that the only thing that might be going wrong is the state that's coming out of your experiment. And I'm also going to assume that, much like this measurement here that only has two outcomes, that you're looking at POVMs with two outcomes. Okay, so can I give you a very simple example where you can write down a verification box that satisfies these requirements? And the answer is yes. So here's the simplest non-trivial example of how these things work. So you've got a box, and it's claiming to be outputting a Bell state. So you push a button, a state comes out, and you think it's a Bell state, and you want to verify that it's actually a Bell state coming out, right? So what can you do? Well, you can do one of three things, I would argue. You could do tomography, so you could take n copies, whatever n you would choose to be, and split them equally among 15 measurement settings, right? A tends to B for A and B in single qubit Pauli. Right? If you do this, then the number of copies you need goes like 1 over epsilon squared, more or less, where epsilon is the fidelity with your target state. Right? That's roughly how tomography behaves. What else could you do? Well, you could do a Bell test. That would be another reasonable thing to do if the state coming out is supposedly a Bell state. So again, take your n copies, split them equally among 4 Bell test settings and estimate a Bell parameter. That estimate of a Bell parameter, you can then infer the state that's coming out of your experiment. And again, if you do this, then the number of copies you need scales like 1 over epsilon squared. So you don't gain much from doing a Bell test over tomography setting. Or you could do a box that looks like this, right? So take n copies, n over 3 of them you measure xx, n over 3 of them you measure yy, n over 3 of them you measure zz. These are all settings that you would have done for tomography anyway. And this Bell state, 0, 0 plus 1, 1, is the unique state that's stabilized by all 3 of those measurements. So as soon as you get a -1 outcome from measuring all of these, you know the red light has gone off on your verification box and the state isn't the Bell state. Whereas if you get lots of +1 outcomes from these 3 measurements, you rapidly gain confidence that the state that is coming out of your experiment is very, very close to the Bell state that you wanted. And in fact, you can show that this thing, just measuring these 3 things that you would measure anyway for tomography, scales quadratically better in terms of epsilon. Alternatively, to get the same epsilon, you need quadratically fewer copies. Does that make sense? Good. So, can we do something for states that are more general than Bell states? And the answer is yes. So I'm just going to quote some results to you now. So we can take any 2-qubit state. So here's an arbitrary, or something locally equivalent to an arbitrary 2-qubit state, pure state. And the scaling you get for this Bell state strategy that looks like 1 over epsilon, quadratically better than these 2, you can extend to any 2-qubit state. If your box is claiming to produce any 2-qubit pure state, you can get a strategy that scales equally favorably over state tomography. And if you have any stabilizer state, so you have a box that's claiming to produce some stabilizer state, not only can you get a strategy that scales like 1 over epsilon, so it gets this quadratic advantage over tomography, you can write down a protocol where the number of measurements you need scales independently of the number of qubits that defines your stabilizer state, which is pretty remarkable. So that means the complexity of verifying a 1,000,000 qubit stabilizer state is equally as difficult, or almost equally as difficult as verifying a 3-qubit stabilizer state. It's also worth mentioning that the protocol I mentioned at the very, very beginning, my very first example of a verification box where you just project onto the state you want, which is the very best thing you could do, also scales linearly in 1 over epsilon. So not only can you show that for these classes of states at least, you can write down a protocol that's significantly better than tomography. You can also show that it's very, very close to being as good as the very best thing you can do. So what that means is introducing these strategy requirements of having local measurements and not storing up lots of copies and various things like that, induce very little penalty in terms of the complexity of the protocol that you're implementing. Okay, right, so I've stated these theorems to you and just kind of waffled about this advantage, and it's still quite abstract, so let me paint you a picture of exactly how significant this advantage over tomography is. So here's a 2-qubit state, right? So it's not quite a Bell state, it's not quite a product state, it's some intermediate entangled state picked kind of somewhat arbitrarily. And I've plotted here, as a function of the fidelity with which you want to verify the number of copies you need. And there are 2 lines that are interesting on this graph. Well, they're all interesting, but 2 that are interesting for this talk. So if you just use non-adaptive tomography, which is this green line, this is how this thing scales. And if you use the optimal local strategy, this pinkish red line. And you can see if you have an experiment and you want to verify that you're within 99% fidelity of your target, you need 4 orders of magnitude fewer measurements than if you'd done tomography. And not only that, it's very, very close to being as good as the project onto size strategy. Small constant factor. Okay, so I also mentioned that I would talk about a box that isn't a verifying box very, very briefly. So this is hot off the press, so I was quite excited to talk about it. So I hope you indulge me for 3 minutes or so. So it turns out that these verifying box with 2 lights on top, you can use to write down a fidelity estimating box. So now a box, instead of having 2 lights on top, has a little dial and it tells you the fidelity with your target state. It turns out that for 2-qubit states and stabilizer states, all the boxes I wrote down that can just verify and output a single bit, you can also estimate fidelity. So here's how it works for Bell state. So this is the Bell state that I presented earlier. Here's the definition of the fidelity. So rho is what's coming out of your experiment. And I'm going to write the measurement settings we had before for verifying a Bell state. I'm going to write the projector corresponding to that measurement as P plus measurement. Then it's really simple to see if you've got nothing else to do in the coffee break besides doing some maths. And if you write this fidelity this way, you can just expand it like this. And so if I just take lots of copies of this state that's coming out of my experiment, and I measure YY, XX, and ZZ, and plug in those estimates, those relative frequencies from these measurement outcomes into this expression, I can directly estimate fidelity. So, not only can I directly estimate fidelity, but this thing is a really simple statistical quantity. These things have rigorously defined error bars, and so I can get a rigorously defined error bar for fidelity that doesn't rely on doing state tomography or something similar. So, I have some data to show you, I guess. So, this is data from this week from a chip that lives up in the physics department, where it can produce, or it claims to produce, arbitrary 2-qubit pure states of this form. So sine theta 0, 0 plus cos theta 1, 1. And you can plot as a function of theta the fidelity of what's coming out of your chip. So in green is the data you get from directly estimating the fidelity using these procedures, and pinkish red is the color you get from doing maximum likelihood tomography. And what you can do is you can write down a protocol that, well, A, it broadly agrees with what you get from maximum likelihood tomography. But not only that, it's much simpler, much quicker, and it has rigorously defined and unbiased error bar. Okay, so I think that's all I wanted to say. If you're interested in verifying things or estimating fidelities, either go read the paper or come talk to me in the break. Thank you.
Questions?
Thank you very much for the talk. Do you know what happened with the anomalies?
You mean in this graph?
Yes.
So this is very preliminary data, and I've been told by my experimentalist collaborator that the chip is very poorly calibrated. So this, these data points are very likely to go away in the next iteration of this data set once the chip is calibrated. I think more interesting is that you get this kind of double dip feature in this graph. So you'll notice that this is plotting from 0 to pi by 2. So here's a product state, here's a product state, and the Bell state is in the middle. And it's not the case that the more entangled the state is, the harder it is to produce. Which is strange. But yeah, these anomalies I think will probably go once the chip is calibrated.
The other Sam?
Hi Sam, thanks for the talk. Can you give an intuition as to why you don't see a scaling with n for the stabilizer state verification?
Kind of, yes. So it's because there's a difference between the number of copies you need to consume and the number of measurement settings you can draw from. So it turns out that these protocols that I write down, for these two and also for the Bell state, this one, they're randomized protocols. So you have some set of measurement settings that you could potentially draw from, and you just roll well in this case a 3-sided die and decide what measurement setting you're going to pick based on that. Right? And it turns out for these stabilizer state strategies, you're measuring from your set of measurement settings are all possible stabilizers, all 2 to the n minus 1 of them. And the number of settings that you can potentially draw from is growing exponentially with n. But it turns out the number of copies you need isn't. So because the complexity of the measurement settings that you're picking from is growing exponentially, that's almost enough to cover the fact that the complexity of the state is also growing exponentially in n.
Question for Alex at the front here.
Thanks for the talk. Lots of people release their data now, raw data from various experiments. I think even I have lots of raw data from doing tomography measurements on these entangled states.
Yep.
I guess you can dig through and you can see whether the fidelities that they've got from their maximum likelihood estimation agree with your method, and it would be really interesting to see. I think there's probably hundreds of papers with this data.
Yeah.
No, I'm interested. Not worried, interested.
Yeah, so it's worth saying that I don't expect the fidelities to be spat out to be different to what you should get from tomography. These two curves broadly agree. But I haven't plotted error bars for the pink data because plotting error bars for tomography is fraught with difficulty. So I imagine you could get the same kind of point estimates but with a more rigorously defined error bar, basically.
With less measurement, with less data as well.
Yes.
Even though it's already been data.
Yeah.
There's another quick question at the back. We're all getting thirsty now.
I'll keep this short. Is there a reason for not comparing it with adaptive tomography?
No. So the reason that we didn't compare with adaptive tomography for these protocols is that most adaptive protocol tomographies fell foul of some of the strategy requirements that we specified in the beginning. So there are some adaptive protocols that allow kind of non-local or collective measurements, some that require more than 2 outcome POVMs, things like that. And in general, it's quite difficult because the protocols are quite hard to define to extract analytic scalings for how these things behave, n like 1 over epsilon squared or n like 1 over epsilon. There's a lot of numerical evidence, but there's nothing that's defined analytically.
Okay, if there's no more questions, I think we'll break for tea or coffee.